So, welcome to lecture series on advanced linear algebra. Today, we will discuss about the annihilating polynomial of linear operator. What is this? What is the meaning of annihilating polynomial of linear operator and what is the use of it? We will discuss in today's lecture also. Let T be a linear operator on a vector space capital V over capital F. Let Fx be a polynomial over capital F. If T is a linear operator on a vector space V, then f of t will also be a linear operator on V, please. If f of t equal to 0, then any other polynomial say gx equal to fx into say rx, okay. Then gt which is equal to, one can write down this is same as rt into f of t equal to 0 also. So, this implies set of all polynomial multiple of f will annihilate t in the sense f of t equal to 0. Okay. So, this set of polynomials will form a basically ideal of the field f of x. I mean this field of basically polynomial algebra, please. So, this set of all polynomials which will annihilate t will form an ideal of the polynomial algebra fx. This is basically set of all the polynomials defined over the field capital F. We know its form A is again a field, please. Now, over this set, set of all the polynomial which annihilate t will be again an ideal of this set, please, over this field also. Not to confuse field, because f is field itself and fx is again a field. It is basically consists of all the polynomials defined over the f, please. So, there exist again ideal means there will be some generators, the least degree polynomials which will also annihilate the operator t, please. If the vector space is of dimension infinity, the vector space may be dimension infinity or may be finite also. The question is, if t is an operator, is a linear operator on a vector space V over capital F, then is there any finite degree polynomial which will annihilate let t. Is there any finite degree polynomial say p which will annihilate t, that is pt will be equal to 0. So, the meaning of the annihilating of the operator t please. Maybe it may not have, we do not know. If the vector space is of infinite dimensionals, but if the dimension of V is finite, then certainly there exists a finite degree polynomial P which annihilate at t. This is the answer I am saying. But the question is, how can you say that there exists a finite degree polynomial which will annihilate t? Let t to the power 0 is equal to say I. Let me define t to the power 0 is equal to identity operator please, and t square equal to t into t please, okay. That is t into t, because t is multiplied to t please, that is all, and t to the power r is t is multiplied r times. What do you mean by that operator is multiplied r times? Basically applied r times you can say. So, we have t to the power 0 belongs to LVV, set all the linear transformation from V to V or linear operator from V to V, t square, t to the power r, all are belongs to LVV. Let dimension of V is n. Then we know dimension of LVV is n square. Consider the set t to the power 0, t to the power 1, t to the power n, t to the power n square, like this. So, B consists of n square plus 1 elements of LVV. Since B consisting of n square plus 1 elements, so certainly this set will be linearly independent. So, B will be a linearly dependent, not independent, because there are more than n square elements. So, this implies there exist C0, C1, Cn, Cn square belongs to capital F such that sigma Ci t to the power I equal to 0 to n square must be equal to 0, must be equal to 0. So, this implies if I consider f of x equal to sigma Ci x to the power I equal to 0 to n square is a finite degree polynomials. which annihilate t. We see that f of t equal to 0. So, existence of finite degree polynomial for finite dimensional space is guaranteed. Whether this is the least degree polynomial which annihilate t or not, that is the next question please. We will soon prove that the characteristic polynomial of the operator t, when t is defined on a finite dimensional vector space, then the characteristic polynomial also annihilates the operator t. See that I will prove it please later on please. So, characteristic polynomial means degree n, which is much smaller than n square plus 1. So, characteristic polynomial also there. But before going to characteristic polynomials, then the question is, does there exist a further minimum degree polynomials which will annihilate the operator t? Answer is maybe yes. So, what is that? That will be basically in terms of minimal polynomial. Minimal polynomial please. Of a linear operator on a finite dimensional vector space please. What is minimal polynomial of a linear operator on a finite dimensional vector space, defined on a finite dimensional vector space? Let T be a linear operator on a finite dimensional vector space, say capital V, over the field say capital F. Since if I go back to the our previous logic that in the polynomial field f of x, if some polynomial is say p x annihilate the operator t, then any other polynomials multiple to the p will also annihilate t. So, it form an ideal in that polynomial field page. Now, since it is ideal in a polynomial field, certainly there will be a least degree monic polynomial which will act as a generator for the ideal place. And that least degree monic polynomial we are defining as a minimal polynomial for the operator t. So, a least degree monic polynomial p over capital F is called as minimal polynomial of operator t, provided 1 p t equal to 0, second if q x be any other polynomial such that q t equal to 0, then p must divide q. Okay. So, this is the definition of the minimal polynomial of a linear operator. In the same spirit, I can talk about the minimal polynomial of a square matrix also. of a n cross n or square matrix. A least degree polynomial P is said to be minimal polynomial of the matrix A defined over capital F, provided P is also defined over F. Second, P of A equal to 0. Third, if G be another polynomial, if G of A equal to 0 for some polynomial G x over F, that is G belongs to f x basically, then P must divide G please. Okay. So, the same definition as in the case of the linear operator please. So, from this definition it is clear that similar matrices have same minimal polynomial. Let A and B be two similar matrices, over capital F. So, there exists an invertible matrix capital P such that your A equal to P inverse BP, A equal to P inverse BP, because A and B are similar. So, that is the definition. From this definition of similarity I have, there exists an invertible matrix P such that A equal to P inverse BP. So, let P be the minimal polynomial of B. So, PB equal to 0. Let P equal to your sigma AI x to the power I equal to 1 to k. So, let P equal to this quantity. So, this implies your Px equal to. So, this implies Pb equal to sigma Ai p to the power I equal to 0 to k. So, this is equal to 0, it is given to us. So, what can you say about the PA? So, PA which is equal to sigma Ai a to the power I equal to 0 to k, which is equal to sigma Ai. We know A equal to P inverse BP. So, this implies A square will be P inverse BP into P inverse BP, which is equal to P inverse B square P. So, in general A to the power r equal to P inverse B to the power r into P. So, I will have this is equal to Ai P inverse into B to the power I into P, I equal to 0 to k. So, this is equal to Since ai is a constant scalar quantity, so I can take out this P inverse. So, I can write down P inverse sigma ai bi I equal to 0 to k into P. So, one can write down P a equal to like this. So, this is equal to 0 already given. So, this is equal to P inverse 0 into P equal to 0. So, we have P is also minimal polynomial of A. Actually, P of A equal to 0 means if the minimal polynomial of A equal to Q, then certainly Q divides P. This implies minimal polynomial of A divides P, In same way, minimal polynomial of B divides minimal polynomial of A. So, from these two only you can conclude that P is also minimal polynomial of A, please. So, we have that minimal polynomial of a similar matrices are basically same. Another interesting results, the relation between the characteristic polynomial and minimal polynomials. Let T be a linear operator on a finite dimensional vector space V over the field F. Let P denote the minimal polynomial of the operator T. Then P divides characteristic polynomial of T and roots of P are the characteristic values or eigenvalues of T. So, if T be a linear operator defined on a finite dimensional vector space V over the field capital F, and if P denote the minimal polynomial of the operator T, then P must divides the characteristic polynomial of T and roots of P are the characteristic values of T. P divides characteristic polynomial T, that is coming as a consequence of our definition of the ideal and definition of the minimal polynomial. Since we know the set of polynomial which annihilate the operator T is an ideal, and minimal polynomial is basically least degree monic generator of that ideal. So, certainly if Q is the characteristic polynomial of the operator T, means I will show later on that characteristic polynomial also annihilates the operator T. So, definitely then P must divide your Q also, because degree of Q will be higher than the degree of P. So, P divides characteristic polynomial is coming as a consequence of the definition of the minimal polynomial, please. Let F denote characteristic polynomial of T. this is we can say fx, this is a polynomial functions. Okay. From the definition of minimal polynomial, which is least degree monic generator of the ideal each polynomial annihilates the operator t. F of t also equal to 0 implies p x divides f of x, please. So, this part is coming as a consequence of the definition, please. Now, I have to show that if for some c belongs to f, p c equal to 0, then c is an eigenvalue or characteristic value of the operator t. P c equal to 0. So, let me do, I can say this one is if and only if, I mean if P c equal to 0, if and only if c is an eigenvalue of the operator t. So, if P c equal to 0, if P c equal to 0 implies P x equal to something like x minus c into q x. So, 0 equal to P t equal to t minus c I into q t. Q t cannot be equal to 0, since degree of q is strictly less than degree of p. Since q t not equal to 0 is a linear operator on V. So, there exists 0 not equal to alpha belongs to V such that q t operating on alpha not equal to 0. So, this implies 0 operator operating on alpha equal to 0 equal to P t alpha equal to t minus c I operating on q t alpha. So, let q t operating on alpha equal to beta. So, this implies t minus c I operating on beta equal to 0, where beta not equal to 0. This implies c is an eigenvalue of t. If c is an eigenvalue, now it is other way please, only if c is an eigenvalue of t, then there exists 0 not equal to alpha belongs to V such that t alpha equal to c alpha. So, this implies P t operating on alpha, which is equal to 0, which is equal to P c alpha, because P t operating on alpha is equal to P c alpha. So, 0 equal to P c alpha, where alpha not equal to 0 implies P c equal to 0. So, this implies c is a root of P. So, you see that the roots of minimal polynomial and roots of characteristic polynomial are same, but the multiplicities may be different please. Okay. So, we see that C is also root of the minimal polynomial P. Another interesting results, if T is a on vector space V over F and dimension of V is finite, let T is a diagonalizable operator on V over a field capital F and dimension of V is finite. Let C1, C2, Ck be the distinct eigenvalues of T, then the minimal polynomial of T will be Px equal to x minus C1 into x minus C2 into x minus Ck. So, this is the product of all x minus Ci factor of linear product basically. This result is coming as a consequence of, if we consider, let W1, W2, Wk be the null space of operator T minus C1i, T minus C2i and T minus Cky, then V equal to W1 plus W2 plus Wk, and any element alpha belongs to V is written as beta 1 plus beta 2 plus beta k. So, now Pt equal to T minus C1i, T minus C2i into T minus Cky, if I consider this operator, then you see that Pt annihilates alpha, Pt alpha equal to 0. How? See, alpha equal to beta 1 plus beta 2 plus beta k. See, beta 1 will be annihilated by T minus C1i, beta 2 will be annihilated by T minus C2i, and similarly beta k will be annihilated by T minus Cky. So, when Pt operating on alpha, this factor alpha, that is beta 1, beta 2, beta k, will be annihilated by some of the factors in P please. So, therefore, Px will be the minimal polynomial of T. So, I hope you have understood the definition of the annihilating polynomial and the concept of minimal polynomials, relation between the roots of the minimal polynomial and characteristic polynomials. If a operator defined over a finite dimensional vector space and having C1, C2, Ck are distinct eigenvalues, then its minimal polynomial is basically product of linear factors x minus C1, x minus c 2 and x minus c k.